Hello and welcome to lecture number, what is it again? 10. And what we are going to be doing in this one is that we are going to be looking at electromagnetic waves in matter. And before we get there, let us start off with Maxwell's equations in matter. Okay. So now I should mention at the very outset is that the form of Maxwell's equations that we had before in relativistic notation so these were Maxwell's equations. And if we were to look at them in the usual form, so in the usual form, let me stress that these are complete. And these do not need any improvement at all. Okay. But when you are looking at materials that are subject to electric and magnetic polarization, there is sometimes a more useful way to write this. So there, for inside polarized matter, there is always going to be accumulation of bound charges and bound currents, where you would not have any direct you won't be able to make any exert any sort of control over that, if you wish. So it's going to be useful to reformulate Maxwell's equations in a form that makes explicit reference to only the free charges and free currents, if you wish. Okay. So let's do that. So already from the static case, from electro and magnetostatics, we know that electric polarization this produces a bound charge, so that is del dot p produces a bound charge rho b, and magnetic polarization or magnetization that produces a bound current, which is Jb. So in the non-static case now, there's going to be one change, okay? One new feature. What is that? So that is any change in electric potential that is going to involve a flow of the bound charge, this must be included in the total current. Okay. So what is going to be the case is that this means that so when we are going to have so let's actually write this down. Any change in electric polarization involves a flow of the bound charge. And this must be included. So let's call that JP. That must be included in the total J, included in the total current. So that means that you have something which is JP, which is just del P del T. Now notice that so this is the polarization current. Okay. This does not have anything to do with the bound current. So now, let's do something. Let's look at the divergence of JP. So the divergence of JP is essentially the divergence of, sorry, that's not rho, that's P del T. So that is minus, sorry, let's do this right, del T of del dot P, which is del T of minus rho B. So del dot JP plus del rho B del T is equal to 0. That is the continuity equation, and this is just showing you is that there is a conservation of the bound charge. Okay, armed with this, let us try to write down Maxwell's equations in matter. But before doing that, let's just see. So total charge density rho is rho free plus rho bound. Total current density J is J free plus J bound plus J polarization. Okay. So the equation above, we know what rho bound is, so we are going to write this as minus, sorry, del dot P, and this is J free plus J bound, which is del cross M. And lastly, we have, sorry, these are all vectors. And lastly, we have Jp, which is nothing but del P del T. Okay. So now, Gauss's law. Gauss's law is what? It's del dot E is 1 over epsilon naught into rho. Now rho is 1 over epsilon naught rho f minus divergence of P. This is written as del dot D is equal to rho f, where you define D as epsilon naught E plus P. This is the same as what we had in the usual static case. Now Ampere's law. What does that have? So that is del cross B. That's mu naught J plus mu naught epsilon naught del E del T. So this means that let's just write this down. So mu naught of JF plus JB plus JP plus mu naught epsilon naught del E del T is essentially mu naught JF plus del cross M plus del P del T plus mu naught epsilon naught del E del T. When the dust settles, you can rewrite this as del cross H is equal to JF plus del D del T, where H is now given by 1 over mu naught B minus M, right? So Maxwell's equations in this form. So Maxwell's equations what do they become? They become del dot D is equal to rho F, it's 1, 2 is del dot B is equal to 0, 3 is del cross E equal to minus del B del T, and 4 is del cross H equal to J of F plus del. In my way of seeing it, this is actually a bit ugly, but because you have both D's and D, H, B, and E, but this is in some sense more useful to look at when you're looking at materials. So since they contain both DH and EB, so you need to supplement these. So you need to supplement these you need to supplement these with something called constitutive relations. So constitutive relations, and these give which express dH in terms of EB. Okay. So what are these when you're looking at linear media? For linear media, this is P is given by epsilon naught psi E into E, and M is given by psi M into H, which essentially means that D is equal to epsilon E and H is equal to 1 over mu B, where epsilon is defined as epsilon naught into 1 plus chi E, and mu is defined as mu naught into 1 plus chi M. So all of these things are here. So you see these are the constituent relations. So now that we have this, what we want to do is we want to write down electromagnetic waves in matter. Okay. So EM waves in matter. So now what we want to do is we want to look at regions where there are no free charges or free currents. So what we have is, in the absence of free, in the absence of free charges or currents, Maxwell's equations become del dot D is equal to 0, del dot B is equal to 0, del cross E equal to minus del B del T, and del cross H is equal to del D del T. Now what we want is, if the medium is linear, as we have just shown above, and homogeneous, that means mu and epsilon do not vary from point to point, the equations above reduce to del dot E equal to 0, del dot B equal to 0, del cross E equal to minus del B del T, and del cross B is mu epsilon del E del T. So you see that these are almost exactly Maxwell's equations in vacuum, except for the replacements. So almost exactly vacuum equations, except for for the replacement of mu naught epsilon naught by mu epsilon. Okay, so what is going to happen is that the speed of propagation of the electromagnetic waves through linear media will actually change. So speed of propagation so V is going to be 1 over root mu epsilon, which is C by N, where N is going to be called, and N is going to be mu epsilon by mu naught epsilon naught, the root over this. This is going to be called something which is the index of refraction of the surface. Okay, so for most materials, what happens is actually mu is very close to mu naught. So n is almost like square root of epsilon r, where epsilon r is the dielectric constant. So light is always, so since epsilon r, so okay, let's write this down for you. So for most media, for most cases, mu is like mu is approximately equal to mu naught is very close to mu. So n, which implies that n is very close to being root over epsilon r, where this is the dielectric constant. Epsilon r is dielectric constant. So epsilon r is always which is always greater than 1. So you see the light travels slowly through matter, more slow through matter than through vacuum. Of course, this had to be the case because you have learned in the special theory of relativity that nothing can travel faster than light in vacuum. So if light started to travel faster faster in matter than in vacuum, we'd be in for trouble. Now, all of our previous results will just go through with the replacement of E naught, of epsilon naught by epsilon and mu naught by mu, and hence the speed of light c by v. So the energy density, if you wish, that is now given by U is just half E squared plus B squared. Sorry, I'm getting my factors wrong. Give me a second. Epsilon E squared plus 1 over mu B squared. And the Poynting vector is S is given by 1 over mu into E cross B. So again, mu naught gets replaced by mu, and the intensity, which was the average of S average, is going to be something that we call the intensity I, and this is going to be given by half epsilon v into E naught squared. This is something that we derived last time round. Now all that we have done is replace the velocity of light in vacuum c by the velocity of light in that medium v. So what is going to be an interesting question is what happens when a wave essentially passes from one transparent media into another, say from water to air, or air to water, or glass to plastic. So what we would expect from our notions of waves on strings, if you wish, is that we would get a reflected wave and we will get a transmitted wave, and that the details of that exact thing is going to be dependent on the electrodynamic boundary conditions. Now let me just mention electrodynamic boundary conditions for you. Boundary conditions. If you have two media, then it's going to be, so there is going to be E1, so that's 1, let's call that 2. So the B1 perpendicular will have to be equal to B2 perpendicular, and the last equation will relate 1 over mu1 B1 parallel 1 over mu2 B2 parallel. So these are so these just relate electric and magnetic fields just to the left of the interface, to just to the right of the interface between two media. So if you wish, there is some, let's draw it with something. So you have one media here and there's something else here. So this is medium 1. So medium 1 has epsilon 1 mu 1. Medium 2 has epsilon 2 mu 2. So this is what is happening between the two, at the interface of these two media. Let's actually make things a little simpler, and let's draw not a perforated boundary but a clear boundary between these two things. So so what we want to do is we want to figure out what happens if there's some wave that comes in this direction and hits this, then so suppose something comes and hits here, what is going to happen? There's going to be something that goes through here, there's going to be something that goes past here, and we will try to understand this in some detail. So this is the incident wave, this is the reflected wave, and this is the transmitted wave. So in the next class we will actually see this in more detail and work this out, and we will figure out what happens in the simple case when you have when there is normal incidence. That's something we are going to address first, and then we are going to be looking at oblique incidence, and we will derive for you a lot of stuff that you have learned in school before in the garb of geometric optics, and you will see that everything boils down to very simply to matching boundary conditions of the sort that I just showed you. Okay, so this was a shorter lecture. I will be seeing you soon for the next one. So all right, so that's it for now.